Remember, we talked about those derivative graphs. We talked about differentiability. We drew another derivative graph and did some pretty heavy notation stuff. You guys remember that? But then we're going to finish our first little section here, 2.1, with something that I think will be pretty helpful. But I think for a lot of folks, it's kind of uncomfortable because I think I mentioned this one time before. How many times have you seen this word in a math class? You have seen it a lot? I feel like most people don't see it very much because isn't it usually find the exact right answer? You know, solve this, don't estimate it, solve it, right? So do you see why sometimes people are a little bit uneasy with, what do you mean by estimate? Does that just mean make a sort of educated guess or shot in the dark and just hope that you hit something decent? You know what I mean? So the word estimate sometimes is a little bit uncomfortable. So the word estimate really is based on the tools that you have at hand. So for example, if you said, hey, I would like for you to figure out the full length or width or whatever you want to call this dimension of this room. Now think about the tools you have at your disposal. Does anybody have a tape measure? No. Even if you had a tape measure, oh yes, but even if you had a tape measure or one of these yardsticks back here, isn't it some degree of an estimate? And think about this. If you took this classic meter stick, is what it is, and you started, like setting it down, and then you marked the end, and then you set it down again, and you did all that, isn't that still an estimate? Because can you be for sure that you set it down repeatedly in the exact perfect spot every single time?
If you drew it.
But still, does anybody have powers of sight down to the molecule? Could you be off by a fraction of a millimeter? Of course, right? So even that is an estimate. You're really restricted by the tools you have at hand. It's like if somebody had a laser measuring device or something, maybe we could say, well, all right, based on the percentage of error with a laser,
but
we could say that it's...
they calibrated it correctly based on their...
You don't know, right? So anyways. So most everything you do is some sort of an estimate based on the tools you have at hand. And so here, number 3, the estimate we're going to do is really based solely on the information in the table. So here's how we're going to do this. It says estimate f prime of 3. So that's obviously the derivative of f at 3, right? The derivative of f at 3 is what f prime of 3 means. But we got to use the table to do this. Somebody remind me what f prime describes about f? Slope. So this is basically saying estimate the slope of f at x equals 3. Estimate the slope of f. Morning. You're good. When x equals 3. So this to me is a really key word, slope. This will kind of guide us what we're going to use to help us estimate this slope at 3. Is there any way I could use the data in the table, the x's and y's in the table, to figure out some information about slope?
Yeah.
What could I use?
The y2 minus y1 over x2 minus x1.
That's right. I hope the video picked that up. It's just delta y over delta x. So there's lots of x's, though, and there's lots of y's. Does anybody have a suggestion as to maybe what would be the best set of x's and set of y's?
Between 1 and 5.
Between 1 and 5, right? Because isn't 3 right in the middle of 1 and 5? So let's do that. I'm going to say that y2 minus y1 equation over x2 minus x1, that whole expression for slope there. If I'm going to use this set of data, which I think makes a lot of sense because 3, x equals 3, is right there in the middle. I'm going to say y2 is 3 minus y1 is negative 6, and the denominator would be 5 minus 1. Does that make sense? Okay, so this would be 9 over 4. So what that is a slope. Can anybody say what kind of slope that is? Okay, positive, I agree. But what type? It is a positive number. Slope of a line, Andy, you said? It's constant. It's not really a derivative, though. Because remember, derivative is the slope at a single point. How many points did I use to get that slope? So it's not the slope at a point. It's an average slope, and it's a secant line slope. Those two, I think, are really good descriptions. So what I could then do is say this, and this is where I'm going to use a different symbol I'm going to say this, that 9/4 is approximately equal to f prime of 3. That is the best estimate I can give here based on the information that I have. I can't really get any more specific than that because the only information I have is this table. That's the best I can do. Could it be that f prime of 3 is like negative 10 million? Could be. I don't know. But based on the information that I'm given, that's the best I can do. Does that make sense? So I've got this little phrase over here, and I think hopefully this phrase will stick with you and will help you remember to do this even when it's like totally out of context. It says, if you can't differentiate, that's fine. Just use the slope of the secant line. Yes, exactly right. So it rhymes. It rhymes, and so hopefully that's why it'll stick with you. Slope of the secant line. So this will come up a lot. Believe it or not, you'll be asked to estimate quite a bit in this course. And if you're looking at a table or maybe some information kind of like a table, and you're like, and if you look at this, I mean, I want you to find f prime of 3. You have no way of knowing what f prime of 3 is because you don't even know what f of x is. There's no way. You don't know what f prime is. You don't know what f of x is. But you got this information about x's and y's for f, and you could use the slope to help estimate it. If you can't differentiate, that's fine. Just use the slope of the secant line. Make sense? Okay. Any questions? Okay. Well then, how is it that we deal with finding f prime if we do know f? Well, that was the subject of the intro video, and there were several rules that we looked at in there. The constant rule, we use that quite a bit. The power rule is used a ton. Do you remember the power rule from before? Maybe in pre-calc, perhaps, hopefully from the video. Did some examples with that. Or wait, where did the video end? There it is. A little check for understanding. What we're going to do here in class today is we are going to do some practicing. Okay? So I believe this is where the video ended. Am I right? Number 8? Yes? Okay. So we're going to do some good practicing, and all those skills that you practiced before, we're going to start to use those a little bit here. So we're going to be finding the slope of a tangent line. We're going to be finding the equation of a tangent line. And this is a good one for sure. This example, I think, will tie it all together for you. So it says, for the function f of x equals x cubed minus 9x, find the equation of the tangent line at x equals 1. I thought what I'd do is I'd start off by trying to illustrate what it is that we're finding. Make sense? So here's a graph over here of x cubed minus 9x. And x equals 1 is, oh, I don't know, right about there on the graph. Does that work? And so that point right there is going to be where the line that we are trying to find, this tangent line, hits the graph just in that one little point right there. That's like my best. I think I could do a little bit better. There we go. That's my best representation. That make sense? That would be my tangent line in red. I think that's fairly, hopefully visible enough for you. So let's talk about a couple of key features here. Does anybody remember what to call that point?
Point of tangency.
Point of tangency is correct. Point of tangency, that is where the tangent line hits the curve. And remember, at that point of tangency, there are two sets of information, two sets of data that are equivalent. So at that point of tangency, the xy for the line, I'll just put it like this, xy for the line, and the xy for the curve are the exact same thing. We've talked about this before. So the point on the line and the point on the curve are the exact same point. But there's one other piece of information similar to that that's true at that point of tangency. Do you remember what it is?
Slopes are the same.
Slopes are equal, yeah. So I'll just put, I don't know, like m of curve equals m of line. So the slope of the curve and the slope of the line are the same. Those two facts are actually true at the point of tangency. Now, anywhere else, they probably are false, right? They probably aren't true, but at the point of tangency, that's true. Okay.
Like if a function is like repeating and it's like the same.
So there could be some other places where
Would it be like, would the function have that same slope? Like
could have the same
point?
slope, totally could, but it would be a different point though.
Yeah.
Yep. So the point of tangency both have to be true, but you could find the same slope somewhere else, for sure. Okay. We good? Let's go ahead and do this example then. So this says, find the equation of the tangent line. So literally, we're going to try to find the equation of that red line when x equals 1. So x equals 1. Can you guys describe, like in terms of the graph and all this stuff up there, what is x equals 1 in terms of maybe some of the key ideas we just talked about? How does it play into that? We just talked about some terminology. We talked about the picture. How does x equals 1 play into that picture? It's better when you figure it out. It's better when I ask you good questions. Hopefully that's a good question. And you figure it out. Where does x equals 1 fit into that? Sure, I agree. And so I totally agree. So x equals 1 is, what's its role? Isn't it part of the point of tangency? I think it is. I totally agree with you. In fact, I could come over here and say that my point of tangency is going to be 1 comma, I don't know yet. It might be. We'll figure it out here in a second. 1 comma something. Well, that's not very useful. I kind of need the y to go with that, don't I? So if I know what x is, but I want to know what y is, how do I do that? Plug it in, do a little input-output. And so I'm going to just use that function up there. So I'll just maybe sketch this in up above so I have a little more room down below. F of 1 equals 1 cubed minus 9 times 1, which is negative 8. So my point of tangency is 1, negative 8. And then when you look at the graph itself, and of course, that's a bit of an estimate on my part, right? Because I'm just trying to sketch in the point. Do you see how the point of tangency is roughly 1, negative 8? Like this point right there. See how it's graphically represented and analytically? Is that good? Okay. So let's just take a step back and think about this. It says find the equation of the tangent line at x equals 1. So really, let's just be straightforward about this. This is asking for the equation of a line, isn't it? So in some ways, this is a very Algebra 1 question. In fact, here in a couple weeks of my Algebra 1 courses, I'm going to give them questions like this. Find the equation of the line, or find the slope-intercept equation line, or find the point-slope equation of the line, given this set of information. I mean, literally, it's the same question. Yours is a couple levels above, because we're talking about tangent lines and curves and stuff, but the end product's going to be the same thing, right? Find the equation of a line. So I have the point of tangency, and I know that the point of tangency is on the line. What's the other thing I need? I have to know the slope. Okay, so then how is it that I'm supposed to figure out the slope at a point, and specifically the slope at 1? What am I talking about? Derivative. That's right. So in order to find the slope of a tangent line, the slope at a single point, that's the derivative, right? So I'm going to have to find the derivative of f, and this is where your skills with the power rule that maybe hopefully you practice on the video would come into play. F prime of x, what do you guys think f prime of x is? 3x squared minus 9. Very good. So that's that power rule coming into play twice, right? 3x squared minus 9. Yes, ma'am.
Okay, I have a question.
Go ahead.
It said, when I was watching the video and it was talking about like nx, because it's like to the power of 1,
Yep.
you would bring a 1 down, it would still remain, but then it'd be to the power of 0.
And what's x to the 0?
1.
So it would be n times 1.
Okay.
Exactly right. Yeah, you spelled it out very clearly. You got it exactly right. It was just the what's the x to the 0 part. It's 1. Good question. Jane, thank you for asking. Anybody else with a question? And so that's one of those questions where I bet Jane was tempted to not ask it, because it seems like one of those little detailed questions like, do I need to ask this? Yes, you do. So if anybody else has one of those little detailed questions like, well, hey, what happened to the such and such or why, whatever, that's a great question. It's just part of the conversation, right? Anybody else with anything like that? We all have those questions. I have those questions now. Like we'll have some staff meeting and somebody will get up and be like, hey, we have the such and such event. And I'm like, can you remind me what the such and such event is about? Because I don't remember, I don't know, or I didn't get the email or whatever. There's just the other day, there was this thing about life groups. And somebody sends me an email and says, hey, you haven't signed up for blah, blah, blah. I'm like, well, what is that? Because I don't think I got the email. And guess what? I wasn't on the email list. So I asked a question. It wasn't even my fault. I asked a question and then they fixed it for me so then I could do whatever I had to do. So please, don't hesitate. All right, so let's talk about what that is. This right here, this is the slope of f of x at any x value. It's the slope of f of x at any x value. So in other words, if I wanted to know the slope of f when x equals 5, all I got to do is plug in a 5. If I want to know the slope of f when x equals 326, Plug in a 326 and tell me the slope when x equals 326. I don't care about any of that stuff. What do I care about?
3.
When x is equal to 1, right? When x equals 1, that's my point of tangency. That's where the slope of the curve and the slope of the line will match, right? And so, bless you, I'm really interested in what's happening at 1. So my next step would be to write f prime of 1, because I want to know the slope at that point of tangency. So then this is just an issue of plug in the 1 in for x, doing a little arithmetic. 3 times 1 squared is 3, minus 9 is negative 6. This is then equal to the slope of my tangent line. Whoops, let me just get rid of that. Equals the slope of my tangent line. And you don't have to put the whole equals ml. I'm just trying to connect it all for you. Hopefully that makes sense. Okay, so remember a few minutes ago I said to find the equation of a line, you got to have the point, for us it's point of tangency, and the slope of the tangent line. And I've got both, right? I've got my point of tangency right here. I've got my slope of the tangent line right there. All I have to do is put it together, and here's how I propose and suggest that you put it together. Please, for goodness sake, use point slope. It's so much easier. All you have to do, remember point slope is y minus a y coordinate equals slope times x minus an x coordinate. That is a legitimate form of a line. Perfectly legitimate. And here's all you got to do. You just go y minus the y coordinate is equal to slope times x minus the x coordinate. And you're done. There is no arithmetic to be done. There is no adding or subtracting or dividing or multiplying. There is no moving anything around. All you do is you go plug, 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 and it's over with.
So you don't want to.
If you insist on slope-intercept form, be my guest. I will definitely never mark that wrong.
Just what do you do from there?
Nothing. That's it.
That's it?
That's the equation of a line.
It looks
Okay, but I don't remember that equation.
You don't have to. I just think this is way easier. Here's the other way. If you don't agree with me, I will try to convert you, but if you insist on using slope-intercept, you're fine. So here's what you'd have to do for slope-intercept. You'd have to say, sorry, I know you're raising your hand, and I'm sorry. You'd have to say y equals mx plus b, and then you'd say y is negative 8 when slope is negative 6 when x is 1. And then there's all kinds of little arithmetic-y things that when you're in the middle of a quiz or a test can go horribly wrong, right? So negative 8 equals negative 6 plus b. You have to add 6 to the other side, giving you negative 2. I know you all know how to do this, but then you still got to put it together. Y equals negative 6x minus 2. There's just more steps. You can actually take point slope and convert it over to slope-intercept simply for solving for y and distributing. Distributing the negative 6 and then you subtract the 8 over. I mean, that's not that hard either. I am a fan of point slope because all you got to do is go plug, 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 done. Your choice. I will definitely not mark it wrong if you...
So point slope is just, couldn't the end technically be on, I know.
No. Hey, you want to see where point slope comes from? It's how easy it is to memorize. Like I said, I am going to try to convert you over to point slope. Just multiply both sides by the denominator. Done. There's point slope. So it's basically just taking the slope formula and rearrange it. So totally up to you, use it or not, but I just think it's easier because it's just 3 plugs, you're done. Okay, yes ma'am.
Okay, so for the point slope one, if you left it as like y minus negative 8, is
That's
that
fine.
Or could
Yeah.
you like change it to y plus?
Totally fine. You remember that world where you had to live in where you, like if you don't reduce a fraction, it's like almost like an unpardonable sin? You don't live in that world anymore? If you want to write your answer as like 3/6 and like live right on it, you're fine. 3/6 is 1/2 in our world. And you want to know what else? You want to know a really bad sin in this class? I better not say this loud. If you leave a radical in the denominator, it's okay. It's okay. We just don't worry about it. It's no big deal. It's no big deal. We'll talk about, maybe we can talk about why they do that sometimes, but anyway. Okay. I'm sure I have some other really scandalous revelations for you, but we'll just share those later. So here we go. Let's do B. So what I'd like to do with B, is it okay with you guys if I just erase all this stuff over here real quick? Because I want to use the graph again. So B says, find the x values where f of x has a horizontal tangent line or maybe tangent lines. We've talked about this a little bit when we drew the derivative graphs. Just looking at that graph of, is it G? No, F. That graph of F, how many horizontal tangent lines would you guess it has? Two. Wouldn't you see one right here and another one right about there?
Could you, like, solve
And that's what we're going to do. That's what we're going to do. Absolutely right. So what I'm going to do is I'm going to recognize the fact that if a line is horizontal, its slope is 0. And so if I want to find out exactly where these horizontal tangent lines happen, I'm going to take my derivative. I'll put a box around it here, this f prime. And what do you think I would do with that f prime equation? Set it equal to 0. That makes sense? I'm wanting to know where the slope of the curve is 0. And so f prime is the slope of the curve. So my first step, this I think what Anna was asking about, would be to write f prime of x equals 0. And once you've done something like this, it is a relatively straightforward equation solve. You would add 9 to both sides, divide both sides by 3. You'd get x squared is equal to 3. And then to finish it off, you'd square root both sides, taking great care to do what? Plus or minus. Yep. So x is equal to plus or minus the square root of 3. And so then maybe the graph makes a little more sense now, because when you look at that, it does appear that there are two tangent lines. One of them is for a positive x value. The other one's for a negative x value. And square root of 3 is like 1.4 or something or other. And so you look at this, and you're like, well, hey, is this, or no, sorry, it's 1.7 something, sorry. So maybe that seems reasonable, plus or minus 1.7-ish. It's like 1.73, I think. Square root of 2 is 1.4 something. Okay. Is this making sense? Are we making some good connections? Any questions? Losing my voice, apparently. Okay. All right. Well, let's see what's next, because I don't know. Oh, yes. I really don't. I don't like pre-rehearse this stuff. Yeah. So because Jane, it said find the x values. So I was only looking for x values. We found where f prime was 0, which is finding where f has a horizontal tangent. Sorry, I did erase that kind of quick. Okay. Derivatives of sine and cosine. Why don't I give these to you real quick, and then we can maybe talk a little bit about the y to go along with that. Let's see, our class is over at 11:20. Am I remembering that correctly? 11:20? Okay. All right, so here we go. The derivative of sine, believe it or not, do I want to? I'm just debating how I want to do it. It is, okay, you already know. I was going to see if you could figure it out. Derivative of sine is cosine, and the derivative of cosine is? Close. It's actually negative sine. Yep.
That's really
Can I give you a little graphical reasoning here? Please check this out. This is going to be a super high-tech graph. Prepare to be amazed.
We don't care.
Whoops. What is that a graph of, to the best of your estimation? Guys okay with that being a cosine graph? Okay. So this right here is cosine of x. And what we're going to do is we are going to estimate this. We're going to estimate the derivative of this. So we're going to use those old drawing of derivative skills to do this. So let's start there at x equals 0. What would you say the slope of that graph is when x equals 0? Do you see the horizontal tangent line? So, like that. So I would say the graph of the derivative of this would be right there. Let's keep building it out. Do you see any other zeros? Like one kind of in the middle and one on the end? Yeah, so here's another 0, and there's maybe a third one out there. Okay. So then let's look at this in terms of positive and negative slopes. So on this lovely yellow section, couldn't you say that the slope of cosine is pretty clearly negative?
Yeah.
And if the slope of cosine is negative, wouldn't that mean that the derivative of cosine is negative?
Mm-hmm.
And if I'm trying to graph the derivative, wouldn't this have to show up below the x-axis? But don't I know that I'm heading back towards the x-axis at that 0? So doesn't it have to do something like That? Okay. But then if you look at this other section that I'm highlighting in a lovely green color, wouldn't you say that the slope of cosine now has turned to positive? It's positive for that whole interval, but like before, I'm heading back towards the x-axis. Whoa, look at that.
That was such a good graph.
Interesting. That last curve was pretty good.
That was
That was
really.
really sad.
First one was good. The second one was really good. I probably should just save this because I never draw things that well. That was a really good one for me. Usually there's like all these squigglies and I got to retry it like 5 times, but whatever.
So that's negative sine.
So think about that, right? So sine, I'll do this in another color. Doesn't sine normally look like this blue graph that I'm drawing right now? Well, see, that's more normal. Anyways, do you see sine right there? I'm so sorry. You know what? All gone. I'll try one more time. Oh, man, my hand bumped the edge. Ah. All right, that's my last try. So if the blue graph is really sine, then wouldn't the purple graph have to just be the flip of that, right? The negative of that? And so this is far from like a really like super ironclad proof of anything, but can you see it graphically? See how that works graphically? Okay. We could do a similar thing with the derivative of sine, but we did one of them. Hopefully that's good enough. You guys have any questions about that? That's just one of those, like I show you the graph thing, maybe it'll stick a little bit better. You just got to know it, right? So if you're a memorizer or you have your way of memorizing things, I'm sure it wouldn't take you very long to get that straight. Okay, so then number 9 says differentiate. And so number 9 is the derivative of pi times cosine of t. Sometimes people get a little mixed up and they look at pi and they think that it's not a constant, but isn't it a constant? Right? It's just 3.14159. It's always that. And so when you do this derivative, remember that constant multiple rule. What you can do with a constant is you can essentially mentally cover it up, do the derivative of the other thing, and then just multiply it back in. So for 9, I'm going to say, what's the derivative of cosine? Negative sine. Then we just like mentally put the pi back in there. So, yep. So it'd be g prime is equal to negative pi cosine, or sorry, sine of t. Does that make sense? It's that constant multiple rule combined with derivative of cosine.
So when they're multiplied, you don't take the derivative of a constant?
Not a constant, multiple.
What is that?
So multiple means multiplied.
Yeah.
So you know what? You bring up an excellent question. Let's talk about this. Can we compare? Let's say I've got two different functions. Let's say I've got g of t equals pi cosine of t, but then over here I also have f of t equals pi plus cosine of t. So on the function on the left, pi is a constant multiple. But the function on the right, pi is just a constant term. So the derivative on the left here would be, like we said before, g prime equals negative pi sine of t. The derivative for the one on the right would be something very different, wouldn't it? What's the derivative of just pi as a term? 0. Yeah, the derivative of any constant. Think about it, like if something is constant, wouldn't it graph as a horizontal line? And what's the slope of a horizontal line? 0. And so the derivative of any constant term is just going to be 0. So in this case, f prime would be 0 minus sine of t. So it's going to be pretty different. So you might have a constant in there, but the question is it a constant multiple or just a constant term? Important to distinguish between the two. I heard a wait. Yeah, so over here on g of t is only a single term expression. So pi cosine t. Over here on f of t, there are two terms separated by the plus sign. Here's term number 1. Here's term number 2. And so on the left, pi was just some number being multiplied times cosine, so it's a constant multiple. And on the right, it's a constant term.
Would we need to write the 0?
Nope, not at all. Not at all. I just do that for a purpose of illustration. Again, Jane, excellent question, right? The one that I guarantee somebody else is wondering that. Thank you for asking.
I was just hoping for the best.
It's okay. Okay, so number 10. Number 10, my experience with number 10, my experience with students is the calculus that we got to do with number 10 is not really going to be the issue. Calculus can be pretty easy. It's the algebra. You see the algebra waiting for you? we can't directly, at least not with the skill level that we have right now, we can't directly differentiate this. We could do the 2 sine x, but the first term, not going to work very well. We haven't talked about how to do a derivative of a fraction yet, and this would even be kind of an extra level up above because of the parentheses and cubed and all that stuff. And so what we're going to do here for this one is we are going to try to manipulate the first term algebraically to get to a better place. Any suggestions on what we could do? Go ahead.
Oh, I was gonna say, so would you have, don't you not have to use like the rule for that? Because can't you just move it, since it's all under the power of 3, like when
You could, yeah. So if
can
you wanted
move it
to,
up?
if you wanted to differentiate it as it stands, you'd have to use the quotient rule, but there would also be a chain rule in there, and we haven't talked about that yet. But this is very manipulatable.
Can't you just move the 2x?
We can move some stuff around, right? That's what we're going to do. So, so Anna suggested we move some stuff around. Is it okay if we do the cubed first before we move some stuff around? So what's 2x in parentheses cubed? 8x cubed. So the cubed applies to both the 2 and the x base. So it's 5 over 8x cubed. And we still have an issue because that x cubed is still in the denominator. And like I said, we haven't learned the official rule for this. So this, I think, where we do what Anna suggested. I am going to move the x up. It's going to be 5/8 x to the negative 3. You guys comfortable with the fact that the x can go, but the 8 can stay? In fact, the 8 really needs to stay. If you move the 8 up, it becomes 8 to the negative 1, and awkward notation for sure.
Is the x in the fraction still, or is it outside?
So you could write it 2 different ways. You could write it, I'm going to erase this, but 5/8 x to the negative 3 is exactly the same thing as 5x to the negative 3 over 8.
Oh, I do not like that.
It's the exact same thing.
That's really.
Web sign-ons changes it.
Why?
Hang on one second. Can I explain why I like this way better?
Yeah.
Because if you do it that way, isn't the 5/8 just a constant multiple? If you do it this way, it all of a sudden feels like this sort of complicated fraction-y thing. But when you do it that way on the left, you can just be like, hey, 5/8, you take a time out. I'm going to do a derivative on the x thing, and then the 5/8 can come back in. Right? Question, Anna?
Why can't you like move up? Like it would just be like 5 times 2x to the negative 3.
You could. You certainly could.
Move it up before you cube it, or no?
You could, but then you'd probably want to move the 8 to the negative 1 that results back down.
Gotcha.
So, it's probably 6 of one, half dozen of another. If you wanted to move it up first, then flip something back down versus simplify it and then move it up, I think you get the same place. Just be careful, right? The only thing that's awkward there is you'd be like, well, what's 2 to the negative 3? Is that 8? Oh, that's 1/8. Or is it 8 to the negative 1? That's why I tend to do it this way, but it could work better for you. Yeah.
Then when did you use like the power rule?
Now we're going to use the power rule. Yep, thank you. So you guys good with the algebra stuff? Okay, so the power rule to find y prime. For the first term, y prime would equal 5/8 times negative 3x to the negative 4th. Sometimes those negative exponents will give people fits, right? 'Cause remember, you're bringing the old exponent down in front, subtracting 1, and negative 3 minus 1 is actually negative 4. Sometimes people are tempted to kind of go the other way with that, so just be careful with that. And then lastly, plus 2 sine of x, the derivative of 2 sine of x would be 2 cosine of x. So plus 2 cosine of x. Here is, speaking of all the scandalous stuff I was talking about earlier, you could just stop right there. There's really, you don't really have to do anything. I mean, let's think about what else you could do. Couldn't you say that negative 3 times 5/8 is negative 15/8? Hey, before you go running down the hall shouting this, let me explain something. But in essence, the answer to your question is yes. You don't have to do this. So think about this for a second. As far as a value goes, how is the thing in the green box any different than the thing with the green arrow?
That one's pretty.
It's slightly cleaned up, but is it any different in value? No. And so if you gave me the thing in the green box as your answer, I'd be fine with it. But don't let that fool you into thinking that you never have to simplify, because within a multiple choice scenario, all of your answers will be simplified. So your powers of simplifying stuff like that need to still be strong. But if it's like a free response scenario and you just want to leave the green box as is, I got no problem with that.
Does the AP test take off points for not simplifying?
No, and they go even further than I do. We'll talk about that as the year goes on. They're very liberal when it comes to that sort of thing. But not with multiple choice. Multiple choice, they are very strict. They simplify everything, and sometimes the simplifying can be the hard part. So you can't just let it go totally, but as a time-saving thing, like if it's a free response and you get to the thing you're supposed to get to and there's like 5 steps of simplifying that you need to do, you don't need to do it. You just stop. So that hopefully is a good time saver for you, at least on part of a quiz or test or something. Good? Questions, thoughts, comments? Okay. So I think there's just one more thing I want to do, if I remember right. Yeah, we got this last little section here. Let me do this. Okay. If you have had a physics course or are having a physics course right now, this will tie in really nicely. If you've never had a physics course, it's no big deal. Everybody knows what velocity and position and height are. But if you, like I said, if you had a physics course, this will like really tie in well. So rates of change, this is where we're talking about more of an application side of a derivative. Remember from before, the derivative is the blank. Instantaneous, yep. So instantaneous rate of change. And remember, that's a little bit of a misspeak there because you really can't find an instantaneous rate of change, just a rate of change over a really tiny interval of time. But we'll use that terminology nonetheless. Average velocity. Any ideas on formulas, expressions, concepts? Excuse me, for average velocity? Say again? Slope of what? What line? The position and time graph. Position versus time. So you're right. It is a slope. But we want to be really careful that we say it's the slope of what. Because if it's the slope of something else, then it's not right. Okay, so let's think about that. If it's the slope of a position versus time graph, isn't slope just change in the vertical axis over the change in the horizontal axis? So I'm going to say something like delta x over delta t, maybe. Change in position, like if maybe something is moving left and right. And maybe we could be a little more generic about this too. What if I said this? Change in position divided by change in time? It's supposed to be a delta, sorry. There we go. Delta position over delta time. Because sometimes we'll have objects that are moving left and right, and so x would be pretty appropriate. Other times we'll have objects moving up and down, so y would be appropriate there. And if you ever take a calculus 2 or a calculus BC, not only do objects move left and right, they move up and down at the same time. And if you ever take calculus 3, not only do they move left and right and up and down at the same time, they also move forward and backwards at the same time and go all over the place. A little more real world, right? Not often that things just go back and forth in a line. They could also go up and down, or they could go back and forth, three space, right? So sometimes people will think of calculus 1 as calculus in 1 dimension, calculus 2 is calculus in 2 dimensions, calculus 3 is calculus in 3 dimensions. That's not necessarily why it's named that, but that's kind of the rough plot. You're good with just living in flatland? 2 dimensions only? Everybody is super flat. If you turn sideways, you can't even see them. Oh my gosh. All right. So then let's expand on this a little bit. Wouldn't delta position, like if you were moving left and right, wouldn't delta position be something like x2 minus x1 over t2 minus t1 for the time? There's one other way to describe this, and I don't know if you guys have heard this word. If you've been in physics, you probably have. Change in position is also known as displacement. So you can think of it as displacement over delta time. So displacement is only concerned with where did you start and where did you stop. So if you think about your displacement for the day, I'm assuming that you probably woke up at wherever you live in your bed, and I'm hoping that you'll end up in the same place tonight. So if you think about your displacement for the day, it would actually be 0, wouldn't it? Right? You started there in your room, you ended there in your room, your displacement was 0. Not the same as the distance that you traveled, right? Because you're here, so you moved. So it's not like your displacement is 0 means that you never moved. You have to think about distance as well. So we'll get into the kind of the details of that later, but I just want to make sure, average velocity, does this make sense? It's essentially how fast can you change position? Like how long does it take you? You know, so if somebody could run like 100 meters and they could run it in 10 seconds, they are world class, right? 100 meter dash, 10 seconds, like that is legit world class. If you run 100 meters in 20 seconds, not world class. You're slow, right? How most of the rest of us are. I don't know. I've heard Anna's pretty fast.
Not in that.
Maybe others. Maybe others are fast too. So average velocity. Does it make sense? Okay. So then take a look here at one of our examples. It says if a billiard ball is dropped from a height of 100 feet, its height and time are given by that position function, s equals negative 16t squared plus 100. If you've had a physics class, that's a kinematic, right?
Oh my God.
Standard kinematic equation. It's in English units instead of metric. That's why it's not negative 4.9. You might be used to negative 4.9 there. This is using feet per second squared instead of meters. Okay, so A says, find the average velocity over the time interval 0 to 2. This is where we'd use our formula. I would say, you had a kind of a homework question like this, sort of, earlier. The time interval 0 to 2, I would say that my average velocity is equal to displacement over delta time. Displacement over delta time. So we are talking about something dropping vertically, so I don't think that x would be a very appropriate variable to use for displacement. You could maybe use a y, or how about an s, right? Because they tell us that position is given by s. So if displacement really is the change in position, I could say then that this would be s of 2 minus s of 0, position at 2 minus the position at 0, all divided by delta time. And what would delta time be for this one? 2 minus 0. Okay, so we do have to do a little bit of work to figure out what s of 2 is. I know what s of 0 is. What's s of 0? 100. Here's my s function right here. So s of 0, you plug in a 0 for t. Make sense? So s of 0 is 100, and then what about s of 2? No, isn't it negative 64 plus 100? Which is 36. I am asking you guys to, well, I see where you're going with that one, Nick. So I'm sorry. I apologize. I can tell I'm going too fast. Sorry. So, are you guys okay with that being our s function, our position function? So s of 2 would be negative 16 times 2 squared plus 100. I'm kind of sneaking it up in there. Is that okay? You do some arithmetic. 2 squared is 4 times negative 16 is negative 64. Negative 64 plus 100 is 36. So 36. And then you can see how s of 0 would just be 0 plus 100?
Yeah.
Okay, so 36 minus 100, all divided by 2. So this ends up being negative 64 over 2, which is negative 32. What do you think the units would be on that?
Meters per second. Or
Not
feet.
meters, feet. Yep, feet per second. Anna, your
That's
question?
so gross.
You don't like feet?
Everything in physics is meters.
I know. We use feet sometimes. Anna, did you have a question?
Yeah, I did. So if there was like a problem like this, obviously like most of the time you need like the derivative to find it. But if like I were to use like on a test like one of them really like kinematic would that be bad?
So basically the way that I write the questions, I want to make sure that the people that have had physics don't have like a distinct advantage over those that don't. So I'll write a question in a way that either I'll give you the stuff you need or I'll kind of force you to use calculus based on the instructions.
Okay.
So not really. Like you might feel more familiar and comfortable with it, but it's not like you're going to be like, I have a trick that not many people
Well,
know.
No, not like that, but like if I used it to like for like a part of the question, not even like the actual answer, like would you like
Yeah.
see my work and like mark it down?
It depends on the way I've instructed you. I might say, show how you use the derivative to find blah, 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 and now I get to see. But then, yeah, so I don't think you'll have a huge advantage other than you might be more comfortable with the form of things. And that's fine. That's fine. Okay, so let's finish with this real quick. So average velocity is the average rate of change of position between two times. So instantaneous velocity would be that instantaneous rate of position change at one point. So when you say instantaneous rate of change, what are we really talking about? Derivative. So in other words, if you want to find a velocity function, we need to find the derivative of the position function. And down below I've written v of t is equal to s prime of t. So the derivative of a position function will give you a velocity function. So what's kind of nice about this is then you can look at a question like B that says, take the same ball and everything, and let's find the velocity not between 0 and 2. Let's not find an average velocity, but let's find the velocity at. Very different, right? 1.25. You guys okay if I erase this stuff? All this up there? Okay. So then, if I'm going to try to answer that question, for B there, find the velocity at t equals 1.25 seconds. I need to find velocity first. So I'm going to say v of t is equal to s prime of t. And this is where you get to use your Powell rule again. So what's the derivative of negative 16t squared? And the derivative of 100? 0. Okay? And then I don't want to know the velocity at any time. I want to know the velocity at 1.25 seconds. So I'm going to say velocity at 1.25 then equals negative 32 times 1.25. And negative 32 times 1.25 is? I think it's negative 40.
Negative 40.
Negative 40. What units would go with that, Anna? I'm just teasing. Feet per second, right?
Oh.
You just said that you dislike feet, so anyways, just
But
messing
if
with you.
it's, so that's the velocity of it, so wouldn't it be feet per second squared?
Nope, because acceleration is feet per second squared. Velocity is feet per just seconds to the first.
If you plug the 2 into a negative dt, just the derivative,
Yep.
you get negative 64, but that's not what we got for that.
Oh man, I wish we had more time to talk about this because we just hit our time. So what Santi said, I'll say this really quick. He said when you plug, are you listening? He said when you plug 2 into that derivative, you get negative 64, but that's different than what we found before, right? What did we find before? The average velocity was? Negative 32. So here's the thing. There's a difference between the velocity at 2 versus the velocity between 0 and 2. Think about it like this. If I go back to my 100-meter thing, Usain Bolt, super fast guy, right? So he ran the 100 meters in like 9.6 or 7 or something like seconds. He started at 0, didn't he? Yet I think if you calculate his average speed, I think his average speed is like about 20 miles an hour over the whole 100 meters. Does that mean at the end he's going 20? Probably going faster than 20, right? Because he started at 0. If he averaged 20 and started at 0, I bet you he was going like 25 or something at the end, or wherever he hit his max speed. So the difference between velocity at 2 versus average across 2 seconds, different. Yeah. All right, cool. Have a great day. See you tomorrow.